So, hello everyone. Thanks for joining this session. My name is Zhimin. I'm the tech lead of Buildbarn team at Snowflake.
And you might remember me from the previous thing, but in case you don't, I'm Richard Woodbury, and I spearheaded the Bazel migration here at Snowflake. Been here for 3 years.
So, in this session, we would like to share our 2-year journey of managing Buildbarn at Snowflake. So in the last 2 years, we learned a lot from the community. We got a lot of support from the community. We really appreciate that. And we would like to also take this chance to share our experience. And we think this will be beneficial and helpful to the community and to the audience here. Yeah. So this is the agenda of this session. We will start with giving the quick overview of Buildbarn scale at Snowflake. And then we will talk about improving the how we improve the scalability of our system, how we improve the reliability of the system, and what we plan to do in the future. And we will have the Q&A session in the last. So to give the quick overview of Buildbarn scale at Snowflake. So at Snowflake, Buildbarn, we have the dedicated EKS cluster. The Buildbarn cluster is one of the largest non-production cluster at Snowflake. So we run thousands of nodes at peak time and hundreds of thousands instance hours per week. So the Buildbarn supports both CI workflows and interactive builds for both Snowflake's non-monorepo and other non-monorepos. So the Buildbarn at Snowflake, we process hundreds of millions build actions a week and hundreds of thousands concurrent build actions during the peak time. And specifically, the build workflow has doubled since April last year. So to support the growth of the build workload, we have built multiple features within Snowflake to expand the Buildbarn. Next, I would like to share more about how we scale our system. Yeah, as a starting point, we initially just followed the example setup from the BB deployment repo. Yeah, the architecture is straightforward. We start with having front end, having cache, and having worker, and having scheduler. Yeah, it generally, in the beginning, it worked well. But at some point, with the growth of the workload, we saw the challenges. And specifically, we saw 2 major challenges. First challenge is maintaining the high performance of critical components, especially cache at large scale. And the second challenge we saw is managing variable workloads in the cost-efficient manner. So yeah, so specifically to explain more about the first challenge, how we ensure high performance of cache at large scale, I would like to give a specific issue we saw, the cache issue we saw when the workload becomes very large. So yeah, so in this specific case, like the original setup, like at some point last year when we had a very large workload, we have many Bazel clients just start read the single jar here. Here we call it A jar in this example. So all of this traffic to read this A jar goes through the front end, they end up with hitting the same cache port. So because of the traffic volume is so large, so this single cache port end up with being failover, and we had a significant performance degradation, and eventually it caused the incident. Yes. So yeah, to solve this issue, we have tried multiple options with some very simple option we tried is horizontally scaling up the cache pods, the cache cluster, and we also tried vertically scaling up the cache, but it didn't work well. So eventually we solved this issue by setting up the read-through cache at the front end. So the idea of using this read-through cache at the front end is, so basically when the Bazel client read A jar, send this request to the front end cache. Front end firstly look up, say if there is existing A jar in its cache. But if it doesn't exist, it will just talk to the main cache and replicate this cache into the front end local cache. So with many Bazel clients reading this HR and those requests hit across all of this front end. So eventually this HR will be replicated to all of those front ends. So essentially original traffic hitting to the single pod was redistributed to all of those front end. So the cache pod, the cache cluster here won't be the bottleneck of the system. Yeah, it worked well and it solved this incident. So with this this setup, like we were able to manage high performance of the cache at a large scale. So next, I would like to share more thoughts about how we manage variable workloads in a cost-efficient manner. So we all know that, like say, the Buildbarn workloads is associated with developer activity. So the workload are high during the business hour and decreased outside of those business hours. So considering this, we start with by scaling worker pools like to a fixed size during the business hour, and then we reduce that size outside of business hour. It's basically the Chrome-based scaling. So it did like with this scaling, we saw two challenges. The first challenge is the queue delays. Basically, workloads could still exceed the work pool size, the work pool threshold, which led to the long queuing. And the second challenge we saw is resource waste. Basically, the worker pool could still be underutilized, and when the traffic or the workload was low. So to solve those two challenges, we built the auto scaling based on the demanding build action count. So the top graph diagram shows the workflow of those auto scaling. So basically, the Buildbarn scheduler emits the matrix of demanding build action count to the Prometheus server, and we leverage Kita, basically the advanced autoscaler. The Kita controller reads those metrics from the Prometheus server, and then calculate, say, the desired number of worker pool size, and use that number to manage the Buildbarn workers. So the graph below shows the autoscaling result. So generally, you can see that the yellow line is the demanding build action count, and the red line is the worker pool capacity. So you can see that with the scaling up, the up and down of the workload, our auto scaling can scale up and down the workers accordingly. So yeah, this auto-scaling worked well, but also bring another challenge to us, the cache pressure caused by the cold start when scaling up workers. So specifically, so when you scale up the new workers, the new worker has empty cache. Then when the new worker start processing build actions, it needs to talk to the main cache to fetch a lot of inputs here. And then considering that, okay, you scale up a lot of workers, new workers simultaneously, then it will generate a lot of cache traffic to the main cache. So to solve this problem, we start with controlling the pace of scaling up. So what does this mean? So I will switch back to the previous slides. So you can see this scaling up event here. So we just gradually scale up our worker. We intentionally control the speed of scaling up. By doing this way, we avoid generating the spike of traffic to the main cache. So the second solution we tried is to add extra layer, a cache layer between the workers and the main cache. So the idea here is that we want to use this worker cache to share the load to the main cache, so that as a kind of extra protection to our main cache. So yeah, as another consideration, we also consider reduce the front end cache as an extra cache layer, but we end up with not picking up this option because we would like to have the front end cache and the worker cache scale separately. So yeah, this auto-scaling work wheel, it gives us the way to manage the variable workload in a cost-efficient manner. In the meantime, with this way, we ensure the cache is still in a good shape. So next, I will hand this over to Richard.
All right, thanks, Zhimin. All right. I'll take a quick moment to pause and just say that I know we have a lot of different shops in the room at different points in their journey on Buildbarn. Some of this information may be obvious to those of you who have felt all these pains. I hope there's a lot of folks though. I know we talked to one person who is in a shop of only 40 folks who are probably starting their journey. I'm hoping a lot of this will be helpful to those of you, but in the interest of just sharing I want to hear all of your war stories too when we have our break in just a little bit. So we all have our different war stories. So high reliability is super critical, obviously. These things are in the critical path for our developers. Performance is reliability. If it's slow, if it's unpredictable, that leads to bad user experiences. And from their perspective, it's unreliable. But it can also end up leading to upstream failures that are hard failures, such as CI timeouts. So, stuck actions that just aren't completing like you would expect, slow cast downloads because of hotkeys like he just talked about, excessive queuing because of no autoscale or poor autoscaling and all of that kind of stuff is something that you have to consider as a reliability metric. So I want to talk about two different tranches here, worker reliability and the storage reliability. On the worker, I'm going to talk about our experience moving from EBS, Elastic Block Store, for our storage, to TempFS. Yes, both of those are ridiculous, but I want to talk about it. And we're evaluating Flash for the worker local storage and also action isolation. On the storage side, I'll talk about, again, EBS moving to local Flash and how we had some challenges with the mirroring configuration. So let's start with the workers. So we wanted to isolate the actions so we can solve the noisy neighbor problem. The reason this matters is because in the default BB deployment configuration, which is, as I mentioned earlier, more of a hello world than a hello load, you have a concurrency of 8 on a single runner container. We're running in Kubernetes. And the problem with that is that it's really easy to blow the memory out of that container and cause incidentally out of memory failures to actions that were innocent bystanders of the situation. This obviously leads to very unpredictable results. It seems nice from an oversubscription standpoint, but oversubscribing memory is fraught. Maybe we could use swap or something, but that's also fraught. So the solution was use no concurrency runner containers. Might be obvious to many, but we ended up learning this lesson the hard way. Partly because we're trying to run very slim. And this is not necessarily a recipe for slim all by itself, because you have to set up no sharing between the containers. You do strict resource limits. But to solve that problem, you have workers of different sizes. So that was our sort of our consideration for trying to manage the cost. But it did add complexity. Now, you might know about the, sorry, let me pull up my speaker notes here so I remember what ISCC stands for. Initial size class cache, the feature of Buildbarn that allows you to, allows it to discover naturally what the resource requirements are for various action shapes, if you will. He talked about the Bloom filter implementation and all that. We decided not to go with that solution out of the gate because you're going to see some of our storage complications. We are not in a position where we can easily persist that information, and reconverging, we understand, can take weeks, maybe even as long as a month. We weren't prepared to do that. So what we chose to do was the kind of the hard work of tagging with the exact properties, the various actions needed to run on larger sized workers. It meant that we only currently have 2 size classes. That's not very granular, but it got us to an okay point, and it definitely solved the reliability story. The other problem is isolating /temp. Obviously, if all of the actions on a single worker are sharing the same temp, that is not good isolation. can also lead to out of disk space errors if things aren't cleaned up. And in our particular case, and I'll get to the TempFS story in a second, it can lead to out of memory errors. But I think the reason why the default configuration doesn't clean up /temp is that it's not a trivial problem when you have the shared temp, because you can't be deleting everything out of temp while you have other things needing things in temp. This implies single action containers. And we had first actually spent some time implementing a cleaner, and we finally found clean temporary directories. This is already implemented in the worker. So if you don't know about clean temporary directories, go straight to go, do not collect $200, save $200 and implement clean temporary directories.
So that thing even works with concurrency, because it's smart enough to only invoke it when a worker goes fully idle, right?
Oh, I see. Okay,
But-
in case you didn't hear,
Yeah.
oh, so that's the part.
Yeah, but the problem is, if you have a cluster like yours that's constantly busy, you never go idle.
Oh, I see. He says that it actually does work when you have concurrency greater than 1 on a single runner container, but it doesn't work it doesn't kick in until the worker is idle, which may never happen on a very busy system. So that is very interesting to know. It might be worth adding this as a default configuration in BB deployment then, because it is safe, even if it isn't always reliable in a busy system. So yes, I might have to change the wording on this slide. Thank you for that. All right, let's move on to storage. So I had to break this saga up into 2 parts. So how it started, we were using EBS because we wanted to avoid losing cache data on the restart of a storage node. Our infrastructure that we are sort of pigeonholed into running into is our internal kind of curated Kubernetes environment. If a pod restarts, it's basically empty dir. You get a clean dir every time. Even when using local flash, that happens. It's a whole thing. So anyway, it was just EBS was just way too slow and expensive. We went to GP3 even, and it just, even with the cost, just accepting the cost, it was still too slow. And the provisioning overhead was very slow. So we're going to the Kubernetes storage provisioner, and this is a read write once, which means that if the pod drops and a new pod comes up, the provisioner might have to wait for some lease to expire before you can actually mount the volume. And it's just like, now we're taking these outages. So we switched to local NVMe, and we used mirroring because we wanted to persist the cache. And the provisioning overhead was fine with that. There's some, but it wasn't too bad. But it actually made availability worse for us. While it actually did improve the story of, or at least it maintained the story of keeping the cache data around, it meant the way it's implemented currently is that if either mirror goes down, writes cannot proceed. It has to wait for both mirrors to be healthy so that the writes can be written consistently. And as I understand it, the reason is so it can adhere to the contract with Bazel that requires that all objects written to the cache for the duration of the build, or were present at the beginning of the build, persist for the duration of the build. And I'll come back to that. We could have tried a blue-green strategy. I think I've heard that you use a blue-green strategy with your cluster, Ed, but there's a lot of complexities with that. But I'll just sort of skirt that and say we decided not to try that strategy. There's also another problem of the mirroring meant that we were doubling the number of cache nodes, and we had a difficult time getting enough AWS inventory for the size of the cache that we needed for our workload. It's a funny thing when you have a big enough shop. You can't treat the cloud like the cloud because you suddenly realize there's actual hardware there and there's only so much of it. Yes.
I assume you used EKS.
We were using EKS, yes.
What CSI were you using for the NVMe mirroring?
No. We're using the BB storage native mirroring solution. So it was 2 independent NVMEs on 2 separate EC2 instances. Yeah. Okay. So how's it going? Well, we're using NVMe without mirroring, and we're just sort of accepting the reality that if a cache node pops, well, we're losing those entries. But it does allow us to use all the inventory available to us, and it's within our cost constraints. But the good news is that this little flag, experimental remote cache eviction retries, It's a mouthful, but what it means is that Bazel will rewind the build if it detects, and it can detect, if there is a missing cache entry during the build. So long as this is a rare event, and so for us it has been, you don't actually see a failure, you just see a retry, and one retry is enough. If obviously this is happening repeatedly because your cache isn't big enough for even the one build you're doing, this is not a solution. But it is implemented, I believe, in this flag is implemented in response to being able to run with smaller, more cost-effective caches, because there's other flags involved for, I think it was called lease extension or something like that. Does anyone have a line on that? Yeah. There's a whole bunch of stuff in there to try to solve this contract problem, but basically this flag changes the contract between Bazel and the storage. And I'll come back to that in the next section. So I want to take a moment and talk about the key location map, or KLM. So this is what allows the BB storage to be able to actually find the objects in the blocks, right? So in the beginning, we were using EBS to avoid the KLM loss. Well, that made sense when we were also using EBS for the blocks that were being stored, but didn't make any sense anymore. But it was left over sort of as a vestige, and we didn't realize it, and it became an IO bottleneck. You might be surprised that where the bottlenecks are in the system. So that's why I have the slide in here. I wanted to let you know that it can be a little bit difficult to discover that something like the KLM and the backing store for the KLM could be the reason why cache lookups are slow, or that maybe you don't know that it's cache lookups are slow. Maybe it's just that actions take a long time to run. Do you know if it's because they're taking a long time to schedule, a long time to fetch, or they're executing slowly because of CPU contention on the node? Like, it could be a lot of things. So some of the overarching story of all this is, how much observability do you have? And this was talked about earlier today as well. The observability into the system is key to be able to run an effective system. So what we did is we switched the KLM to in-memory. It was very easy. We didn't have to do tempfs or something. There's an in-memory implementation, and it was sufficient, and we're okay losing the KLM because we're gonna lose the block storage anyway if the node restarts. So it's a perfect marriage for our very strange setup. And problem solved. Like, the KLM is not an issue anymore. So take a look at your KLMs if you haven't. So here's the slide on observability. As I said, monitoring and alerting for all of the dimensions of your system, including network bandwidth, are just really, really critical. We were running blind to network for a long time because of the constraints of our platform that we're running on. That visibility was night and day to us being able to actually understand what was going on. Also, gRPC latencies are a really critical health indicator. You want to find out before your users tell you that things are bad, right? Ed mentioned that there's so much information exported through the Prometheus endpoints. It's all there. Maybe we talked to the panel about maybe we could add some alerting suggestions and things like that. I think that would be a good outcome from this event today, is to add some of those to help everyone have an improved observability story. And if you've got your own stories where you said, oh yes, this metric in this particular way was really great, I hope that maybe you'll raise a PR against that repo with another entry to the dashboard or another alert. So what's next for us in our Buildbarn story? Well, we want to get mirroring back, even though it costs something. We'd like to have it back, but we want the high availability aspect of it. And I mentioned that flag that I will not repeat because it's too many words. Because the contract is fundamentally changed with that flag, I think we can accept writing to, and correct me if I'm wrong, maybe I'm missing something, but we can accept writing in a degraded mode. Yeah, I am getting kind of this from Ed. It would not be, it would obviously not be the correct default behavior for the system, because it depends on your Bazel builds running with this flag. Otherwise, you're going to get build failures. So we want to do that experiment. Obviously, it doubles the cost, but it depends on what your trade-offs are. And it would be very simple to do rolling updates on the storage at that point, even in the condition where you might lose cache entries. Because in our experience, the cache gets repopulated pretty quickly. Maybe that's a function of just simply the size of our system and how much load we get from our CI systems. It all comes back really, really fast. So the other thing is, we're still trying to get onto fuse workers. And, it's interesting that on your new setup experiment, Ed, that you're not actually going to implement the native mode anymore. I'm kind of fine with that, but we've had some difficulties with the fuse workers. If you don't know, if you haven't tried using the fuse mode, what that means is that instead of it having to write a bunch of hard links into the build directory for every action, it's able to just sort of present a view that's more or less set up instantaneously based on the input specified in the action request. And one of the best things about it is that you can start running the action without having to download the entirety of that input set, which might be substantially overspecified, especially for things like tool chains. So it might be 100,000 files in your tool chain. You need to, actually open, hundreds of them in order to make your build. But the challenges for us is that we have a lot of tests that are very persnickety about file system specific behaviors. And maybe that's just the nature of the Snowflake product. That it's highly optimized to run on a variety of circumstances in a 3-cloud setup and all of those sorts of things. So one of the things that though that was not implemented until recently was M-time support for things that you're writing as build outputs. That got accidentally fixed by switching to the what's it called, the write through mode, because now the kernel's responsible for maintaining the M time. So it was sort of like a happy accident, but that broke rules for NCC. We couldn't run make inside of Bazel because autoconf was kind of like, hey, your file system's bad and you should feel bad.
Patches are welcome.
Yes, I know, but we were going to until we realized you had fixed it by accident. But yes, we were ready. And so I'm still working on trying to deal with some performance issues that we're having. It's probably something with our configuration, but I'm deep inside of like kernel land trying to figure this out. But the promise of the right behind mode, as written right here, is that it actually improves the performance of, say, large writers like packaging steps, linking steps, and whatnot, whereas Fuse is sort of notoriously poor at dealing with those sorts of things because you're having a context switch through user mode. But the right behind mode was implemented like a year ago, maybe half a year ago. It is able to record all that information in the block cache in the kernel, and then the kernel synthesized the writes in bulk to the Fuse implementation. So that's super cool. So yes, I think most people should be using Fuse. If you're early in your process, I would say just go straight to Fuse and don't look back and fix all your targets and don't work with it, rather than what we're doing, which we're coming to Fuse late and having to deal with the onslaught of things that are already there. And it would have been nicer if we'd done it sooner. Okay, that's what we've got. So let's take, I guess we're a little bit over time, but maybe we can take a few minutes for Q&A before we break.
Yes, here's what I'm gonna suggest. We have a terrible choice between having more questions and then starting eating. So what we should do is take a few quick questions. We'll remain here, ask more questions, and then we'll come out and eat with y'all. If you wanna stay and ask more questions, more conversation is better. So first question.
Mentioned switching to instance types that had attached NVMe for storage, and then earlier you talked a lot about, or could you talk a bit about how a lot of front end now had a portion of the cache, and you had intermediate cache as workers also had a cache, and then issues with getting instances. Did you guys have to pick different instance types for all those different pieces and like tune according to how much storage you needed at each level?
Yeah, I think like we kind of like dance with the limitation. Like we try to balance, say, cost, inventory, and the instance type. Yeah, so yeah, a lot of things need to take into account. It's not really like a simple choice or simple decision.
Yeah, one of the problems that we've had, especially with the front ends, is kind of figuring out, okay, obviously they have a lot of bandwidth requirement, but they don't have a lot of CPU requirement. We're kind of underutilized badly on the front ends right now. But they also need to have the local cache storage so we can have that sort of L1 cache, if you will. We could move it out and have it more of an L2 cache, but then that's sort of its own expense. And it's like, yeah, so picking the right instance type is non-trivial.
Yeah, so yeah, I want a little bit here, like say what we take into account is the like networking and also CPU and memory ratio. Cause for example, when we start working on Fuse, we take like we will move the TempFS to the NVMe. Basically, then we'll take we don't need to use a big amount of the memory. Then that also triggers the instance type change and also potential cost saving. Yeah.
Oh, actually, I want to throw in one thing quickly. I realized I didn't make it into the slides. The reason we moved to TempFS was because we're having performance issues with EBS. And I said, well, let's just try TempFS to establish a baseline. And of course, that became the permanent solution. Just burn the RAM and have the fastest file system known to anybody.
I just quickly wanted to mention two specific things. With regards to, like you said, front end doesn't need a lot of CPU. Important to mention that if you use ARM64 instead of x86, it might even use less CPU.
Which one are we using?
The reason being that ARM64 out of the box has some pretty good SHA-256 hardware instructions, right? Whereas on Intel, you need to use AVX, and then it runs a bit better, right? But there, ARM64 works really well. But with regards to like the key location map on EBS, important thing to mention is I never really optimized the key location map on disk because I never use that. I only use like a persistent key location map for like client D and some on-prem caching. And there the performance, demands weren't as high, which unfortunately means that the key location map is currently protected by a single reader-writer lock. And that means that if it's disk-backed, then you get some hangs and everything will suffer. Would be nice if that would be somehow be implemented as a lockless design, but considering that the key location map is a hash table where we're actually doing reordering of entries as well to like push older entries deeper into the hash table so we can, automatically let them disappear, magic. That means that it's not trivial to sort of make it lockless. So
if you're not, as I understand, you are preserving the block storage though for the cache entries, but you're not preserving the KLM on a restart. Is that what I understand?
No, so everything gets lost, right?
Oh, so you're in a lose everything mode like we are, but you run like a blue-green kind of setup?
Yeah, I use mirrored
Okay, all right.
setup. Yeah, but indeed, like configuring it so that, you only use disk, because you don't have enough RAM, right? And keep the key location map and RAM, that's the way to go. Over it. So were some other questions?
Thank you. Might have missed it, but did you consider using the instance storage as a hyperconverged setup with something like Rook Ceph that can provide you DVCs, can do some reconciliation, a little bit dynamic involved?
I don't think we ever considered using any storage platform other than sort of the standard Amazon set of things that they provide. I mentioned Rook Ceph earlier, but we don't use it here as something that I use for my own personal cluster because I'm crazy. I think that given my perspective is that given kind of the way Buildbarn is architected, you're better off trying to use the barest thing that you can and using Buildbarn's own facilities to manage things like replication and whatnot. I think that getting consistent replication on like a shared block device on Rook Ceph, I don't even know if it supports it. I think you would have to have an out-of-band synchronization facility to do that, or you'd have to take like something equivalent to a SCSI lock. It brings me back to the days when I worked with fiber channel SANs and stuff like that. So I think you're probably going to have a better experience with just doing, direct block device access.
Yeah, those systems are likely too strong.
Yeah, exactly. It'll be kind of similar to the KLM like global lock kind of problem where, yes, it's consistent, but at what cost?
So you mentioned front end, you mentioned storage, schedulers is vibing and didn't have any problems whatsoever.
So what was the last part?
Your scheduler is fine, it's just
Oh,
vibing,
yeah.
didn't have any problems whatsoever.
So far, the scheduler has been just fine. I think the CPU utilization, our scheduler, is somewhere around like 20% on a bad day.
Yep.
Yeah.
20% of what?
Of the CPU of the whatever machine we're on.
I need to look up, but I think like, as I mentioned, like just a 20% usage, CPU usage.
It's probably on an 8XL or something, right?
I think it's probably small,
Even smaller than 8XL, yeah.
Gotcha.
Yeah.
And are all of your workers, is it one pod of Buildbarn worker per node, or is it like multiple?
Yeah, we pretty much lined it up so we don't run more than one worker per node. That gives us good cache amortization. Local, what I like to call the L1 cache amortization.
Gotcha. So when you're mentioning those worker caches, those are on the same node?
Yeah, because that's just the standard cache that you get because you have a worker. Every worker has a local
Gotcha,
cache. We didn't implement an extra cache.
Okay, thank you.
Oh, and also running the front end caches the way that we do in a sort of L1 style where it's co-located with the front end gives you sort of this natural scaling property if you bring the workers up and down. Another reason we didn't implement like an L2 cache strategy like we did for the workers.
Yeah, so there's not a question, but like, great to hear that you only need a single scheduler, right? That was also my experience, right? You can just throw a lot of stuff in it. The reason why the scheduler scales relatively well is that the locking that it has is incredibly fine-grained, right? So, 90% of all the CPU cycles that the scheduler needs to burn is all like, protobuf juggling. And all of that is done generally outside of critical sections in that scheduler, right? So it's, whenever you send an execute request, that's when it's like messing around with protobuf and doing all the expensive stuff. And it's just picking up the lock quickly, inserting some stuff in data structure and then unlocking it. So the nice thing is that it, to a certain degree, scales past a single CPU, right? But you don't need that many cores even, right?
And we do see it very neatly use like several CPUs very, very handily without any observable latencies. Like even just using the scheduler web interface, you would expect to observe some hitches every once in a while if there's a lock contention, but we don't. Like,
oh, yeah, so there's something I do need to warn you about.
Uh-oh.
Right, so inside of the scheduler, when like all you have is a hammer, everything looks like a nail, right? Yeah, that's how the saying goes, right? So I'm using binary heaps, the data structures all over the place. I don't know why. They worked, right? But in the scheduler UI, we need to, so for people who know what a binary heap is, every sorted list is also a valid binary heap, right? So whenever you open a scheduler page, we need to show stuff in sorted order, right? So what happens then is that we just lock the scheduler, sort everything that's in there, and then we can just display it in the right order, right? And then we don't need to copy stuff around. We're just doing an in-place copy, mutating the entire scheduler to sort it, but the scheduler doesn't care, it keeps on running. But that does mean that like if you have a lot of stuff in the scheduler and just like Command R, or F5, whatever operating system you use, you're basically just picking up a lock and calling sort across all the data that's in there. So,
so you're saying, I know how to DOS our scheduler now.
yeah. Just open up like the list of all actions, right? The one you have to top, and then just keep on refreshing it.
As
So
crawler.
Yeah, until
Don't give
tomorrow
up.
when we remove
Yeah.
the scheduler web UI from there.
now you know.
Thanks for that warning.
Oh, sorry.
All right,
This also applies to like using the build queue state gRPC API, right? Because what the scheduler shows, it's just getting it through that gRPC API. So also via gRPC, don't use the functions to like list all the operations. It's pretty intensive.
So now that we've been talking about this, I'm becoming a little bit nervous because one of the rules, there's many rules of building systems at scale, but one of them is don't brag about how your system scales, because that will be your next page.
do we want to go ahead and kind of release people to go?
Yeah, last one.
Okay, all right.
Yeah, I was just gonna ask how you prototype your changes. So we've come up with a lot of the same solutions that you have. We have a real hard time testing and prototyping. So do you guys have any good strategies or recommendations for that?
You want to talk to that? You want to, all right.
I think the sales conversation is a good one. We can take that in the group.
The what oh, yeah, okay, all right, yeah. What do you mean by that exactly?
We test?
No, what do you mean by the group?
We're gonna go have food and chat.
Yeah.
We should like make a circle and talk about this.
Okay, all right. Well, this will be an outside chat about how to test your changes. All right, thank you very much. Really glad to see as many people here. Can't wait to talk to all of you.
Thanks, everybody.